Hi, Benjung. Hello, David.
Good morning. Hi, Mark. Hi, David.
Hi.
Give others a minute or so to go. Let's see if we get a quorum. Okay, I said let's get going and see if others settle in. So today is the SIPI kit. I wanted to share briefly with you guys. I made a little bit of progress um, on the SIPI kit. Basically, I started with the file layer and started describing some of the properties of a file, beginning with, give me a second. I guess we will see this. Oh, okay. Hopefully. Okay. Oh, I guess I'll start over. Um, okay, started capturing some of the parameters that we talked about. The file layer. Basically, thinking about this, there is the type of the file, whether we're talking about serial or parallel. Then, in terms of data rate, there's general. You've probably seen sometimes a file expresses data rate of gigatransaction per second. Sometimes it expresses the gigabits per second. I thought it would be good if we standardized on gigatransaction per second. Mostly because some of the serial interfaces, the number of data bits transferred is a little bit less than the electrical bits transferred, right? And it may be due to actually it could be even more, right? Depending on the encoding scheme. So in general, the bits per second is different than the transaction per second. Transaction per second is purely uh, electrical definition. Now, what gets transferred and how much does the gigabits per second? So to since we are the purpose of this definition is really to look at the electricals and the electrical simulation of that. My expectation is that the high-level simulation will figure out the encoding scheme, what this need to be transferred, and so on. But the basic transmission is the gigatransaction per second. That's how do I say it? For parallel signals, for especially for that-to-that interfaces, they are the same gigabits per second and gigatransaction per second, but for serial they are not. So that's why I thought it would be good to standardize on gigatransaction per second. I think Intel also uses gigatransaction per second as their standard to express uh, the electrical data rates. So any thoughts on this? Yes, no? Agree? Disagree?
I think we need to clarify it in more details.
What do you mean? Can you expand a little bit on this?
Yeah, we need to expand a bit, elaborate a bit.
Sorry, I didn't get this.
We need to elaborate on this a bit. So that's if they would like to convert the data from gigabit per second, how should they do it? Provide an example scenario.
Oh, okay. Yeah, I kind of in this description I kind of mentioned that this is really the role transfer rate. But okay, I let me take a note. Okay. Okay, yeah, let me think about this a little bit. Okay, I think that's fine. Yeah, let me think about it for a little bit. Then we are looking at the encoding of the signals. Then we have a list of which are the data pins. And we have a definition for how clocking is done. There's basically two parts to clocking, depending on the type of file and how it's transferred, right? So I think I need to expand a little bit here. My intention was in a way to list the general list of properties, and then below get a little bit of more details about specific examples, right? Because clocking scheme could be, I guess, differential and source synchronous, right? Both at the same time. So it's kind of what I'm trying to say is give some examples when what is applied and what would be a valid definitions. Then what are the clock pins on that file, if any, right? This applies to mostly the split between data pins and clock pins applies to parallel interfaces. Then serial interfaces, I need to think a little bit how that would look. Whether it's going to be just pins, which are the two pins that are applied to the serial interface. I'm assuming it's different. You'll notice here I have kind of section 12. The way I thought about it is, okay, this kind of describe the interface, and then here are the parameters for this interface, right? So what needs to be used. What this interface does, I mean, what are its limits? So starting with data bits queue, there's really two. Let me build this up a little bit so that it's obvious. Basically, there's two parts to this. One is the transmit side and one is the receiver side. Each protocol, like the Google, meant to capture any standard definitions and or actually the characterization data on the file. Meaning a standard may define certain limits for some of these properties. A file may be an actual file, right? So the solution may end up being better, which would be helpful for implementers because it's going to give them a bigger budget to work with. On the other hand, if there's any customization, a file may actually be worse, but as long as both sides understand it's worse and the overall limits are met, it's all good, right? For example, on the receiver side, a standard may specify a certain limit for data skew that the file may be able to handle, but an actual file may be able to handle bigger limits or smaller, right? So in one case, it will be advantageous to the implementer because it's going to make their life easier. On the other case, it's going to be more difficult. Or maybe it doesn't matter depending on how the routing is. So this is kind of the split between transmit and receive side. So we're talking about data bit queue. I can just get the people. Okay. Then we are talking about the word and bytes queue. I know some memory interfaces, especially the very wide ones, they have different limits on the byte level bit queues and then on the word level bit queue, mostly because each byte may come with its own strobe signal. But then, right, so that's handled the byte level skew, but then at the word level, you still want some sanity, right? In terms of how much skew is there between the bytes in the word. So there's two limits about that. And then below, I kind of captured, right, the data to clock skew. What is the clock timing mismatch, right? In parallel interfaces where we have two signals going through bit, one positive, one negative. There may be a mismatch between these two signals. And the question is how much can the transmit side, what does the transmit side do? And what can the receiver side do? In terms of understanding where the clock is and so on. Then there's the clock jitter. There is, I didn't get far enough to describe these, but basically we're looking at the driver impedance.
David?
Yes.
Sorry, I have a question back on the word and byte skew.
Okay.
Okay. So you mentioned that this is defining the acceptable skew limits. So is that something that again depends upon whether it's a receiver or a transmitter? Because it seems like if it's a transmitter, you would be describing what is the skew of the transmitter. And if it's a receiver, you would be more interested in, okay, what limits of skew are acceptable? Is that right? Or
Yeah, so yes, that's right. But keep in mind this, right? There is two, I guess there's two sides to this, right? Even on the transmit side, a user may decide to populate the protocol level definition. I'm sorry, let me take that back. A user may decide to describe the standard level requirement, right? What are the limits that the standard defines in terms of transmit side data skew, data bit skew, right? A phi may end up better or not, right? A phi should fit within that,
okay.
right? Now, a user may also decide, hey, here is the standard. So whether we have characterized this, and our phi under worst case conditions or typical conditions or whatever conditions has this much of data skew, data bit skew,
Mhm.
right? So that becomes, in my mind, the way that's going to work is so that data becomes as a input to the simulation when they're simulating, when we're doing this discourse simulation and looking at different bit skews, right, they take that into account. Then the simulation will take that, propagate it to any routing, and then on the receiver side, you have the data that says these are the limits for this phi, right? So any signals coming in, any right with their skew must be this much, whether that's the standard definition or whether that's the definition from the standard or whether that's the based off of actual silicon that's characterized that shows hey we can actually follow worse skew or no we cannot even tolerate that our the skew needs to be tighter. That's a different problem. So you are right. On the transmit side, that's kind of like a data. On the other side, on the receiver side, it's a limit that must be met.
Okay.
Right, and it gets a little bit trickier when we start talking about bidirectional. Um,
Yeah, I see.
right.
Okay. Thank you.
Yeah. Yeah, HBM has this. They have a clock and they have a strobe for each of the bytes. And that kind of gives you the limit against the main clock and against the strobe. For the byte.
Okay.
So this is pretty much how far I got. Looking at below, kind of what we've talked about before, this guy captures most of this stuff. Let me actually do like this. Okay. Okay, so these are captured. These are captured. The slew rates, I'm not getting to those yet. Driver impedance, and so bidirectional links. Bidirectionality, I think, is going to come from the pin definition itself, right? Unidirectional pins will be already be defined as inputs or outputs, and the bidirectionality is going to come again from the same definition. In some cases, it's going to say these pins are in out, right? And that's how we'll know these are bidirectional. So I'm not exactly sure how much we need to do this. Maybe there's the full duplex versus simultaneous bidirectional. You need to think about that a little bit. Equalization, I think I added that, yeah, transmit equalization. That's important at higher speeds, and it's mostly yes, no. It's already defined, the standard defines it, and I don't think I need to provide any additional information. Yeah. So this is kind of my how far I got in recapturing all these parameters from the world. Together, welcome to make edits to this document. In case you don't know where it is, let me post the link in the chat again. Okay. So please feel free to edit and provide your input. Okay, so this is what I have on the SIPI side of things. Any thoughts?
Well, it's nice that you're filling that in. So if I follow you right, one of the things to understand then is that this document can serve two purposes. One is that you can use these different properties you're defining to describe a standard for interconnect. And two, you can also use this to describe specific implementations of inputs and outputs on chiplets. Is that the correct understanding, that the intent is to serve both purposes?
What was the first purpose again that
The,
you mentioned?
to describe the properties of
Yes.
a standard interconnect system.
Yes.
Okay.
I think you understanding it is correct. Basically, there is right when you think from designer's point of view, they are supposed to read few documents. And you know that correctly. One is the standard that tells you what are the electrical parameters for this property, right? For the site property. And then they'll take those and put them into their simulation tools and run simulations, right? We want to kind of automate that manual entry process. Now, not always do the standards are that simply. And I'll single out HBM here, where they do not go into very deep level into the electricals, right? They describe some of the skill requirements, but for example, don't go into describing slew rates and pre-emphasis and all that stuff, right? And what are the so some of the little bits and pieces are missing. Those I expect to come from the actual vendor when they have implemented it. And what are those additional properties? My hope is that what I want to enable, and that's part of my hope, is here actual implementations of those standards, 5 and 7 of those standards, and end up being better than the standards. And to provide a description in a file format to tell users what the actual values are, right? Because that makes life of the implementers a lot easier, right? With, for example, the receive side can tolerate larger skew. It's so much easier on the implementation of the package, right? The second part of this is, which I maybe have to have fun with, is when there's a customization to IP, to work in modes which are not defined in the standard. But those, and the reason for that is they may be providing lower power or maybe providing higher speed. For a user to be able to describe that, such that me as an implementer, one, I know how to implement the process, and two, I would be able to tell whether the other side can operate in those conditions, right? That initial, I think the byproduct of all of this is going to be the ability to kind of match two chiplets and see whether at least at the electrical level protocol they are compatible. Right? Because marketing people will always tell you, yeah, they're compatible, but once you dive into the actual electrical limits, they may not be. Right? So kind of to provide a machine readable data that can go into that next level of analysis. Boy, that was a very long answer to your short question.
No, that's okay. That's helpful. Thank you.
Yeah.
Yeah, I have a quick question. So yeah, I joined this this work stream. I mean, a little bit, but this is probably only my second meeting here. So I'm trying to learn and understand a little bit here and see where I can help and contribute. So I see that this document here is right. It's related SIPI. I'm looking at the document. I see a lot of signal integrity. I do not see or at least the PI portion addressed. So what is the intent of the document when it comes to PI?
Thank you for asking this, and I think you can help us define that. We actually struggled a little bit about what exactly do we want to capture for PI. And the two immediate data points would be needed for any implementation, right? If I'm package designer, the two pieces that I want to know is how much would be my power and ground plane impedance and how much capacity do we need to have. Typically, when you have somebody who is providing you a die, they will tell you those two values, right? Because when they designed that die, they thought about what the package needs to do and would know, hey, I simulated the power integrity of my die, assuming this much impedance and this much capacitance on the outside.
Yeah.
Right. And that typically gets put into a data sheet, and a human goes and reads a data sheet and says, oh, okay, this is how much capacitance I need to have. I need to figure out how to do it. So we want to automate that process. Now, you are the power expert, I believe. What else do you think would need to be provided to you?
I think it's something for the analog rails, it's for the analog, especially if we are talking about PHYs, right? So the noise level is very sensitive, and I was thinking that we will need each die to specify their noise mask or something like that, like provide the noise sensitivity with frequency. So that
noise sensitivity with frequency for analog supplies. What does that look like? I've never seen
that would look like a graph with voltage peak to peak versus frequency, for example.
Okay, so
just an example of where that could be looking like.
Okay, basically a graph with voltage peak to peak versus which frequency?
The frequency of the noise, that's the voltage supply that the IC will be running at, right? So meaning not the IC will be running at, the interface of, okay, let me put it this way, right? So the interface, the voltage supplies for the analogs, right, for the PHY, because that's all the clock and the CDR depend on that. You say, okay, if you are the voltage that I'm supplying that are supposed to be received, should have a 5 millivolt peak to peak over the frequency from, I'm picking a number here, from 1 megahertz to 10 megahertz. And then if I go from 10 megahertz to 100 megahertz, I can tolerate a 10 millivolt peak to peak. For example, that would be a definition like that.
Okay, so yeah, okay, so this is the frequency of the supply node.
Yeah,
So
yes,
basically-
yes.
Okay.
The noise that is riding on the supply that's coming to my chip.
Okay. Okay. And this is a requirement from the chiplet, right?
Yeah, that would be a requirement for the chiplet, correct?
From the this becomes a requirement from the chiplet vendor, and then the next level guy needs to figure out what does that mean in their domain, in their system.
Yes, so the system, the chiplet vendor will put that as his requirement, and the system vendor, the system designer, right, package designer, board designers, and system designer in general, they will design their system to meet those requirements.
Okay, and let me ask you an additional question about this. Would that requirement be dependent on the actual interface speed, right? Let's say you have a DDR interface, right? And you can run it at different speeds. Obviously, right, you want to meet it at the worst case, right? The maximum speed, basically what the supply needs to give. Would you also go and say, okay, at least would the requirements be different for lower speeds? Or once it's met at the maximum speed, it's done?
Typically, that's the way it is specified. If it is met at the maximum speed, that is where it's done. It's going to work at the lower speed. Yes, so yes, typically that's the way it is supplied, because it is supplied. It is only one mask is given, and that mask will cover the entire frequency that the chip will be running at. So, like I said, for example, I mean, the mask will not have like one single corner, right? If it is like a complicated design that's going to run at multiple speed, the IC designer will study their part, and then they say, hey, if I'm running, let's say DDR, I'm running at 6400, then I have a clock rate that is, I don't know, 3200. It means that my spectrum of tolerable noise is going to be over this, and then it's going to be this millivolt peak to peak. But if I'm running at 9600, then the spectrum is going to change a little bit, and then the vendor will provide another corner on their noise mask for the level that will be tolerated at that. So most vendors have only like two corners, meaning, hey, I'm going from 0 to 1 megahertz, and then from 1 megahertz to 100, and then above 100. Some other vendors, especially on Ethernet, are a little bit more complicated, where they provide multiple corners. So it's really going to depend on the IC. There's no one single frequency, one single answer there.
Yeah. What I was thinking is whether we need to consider the modality of the chip or not really, right? If it's just a interface dependent cable, that's fine. I was thinking whether within that interface, if we need to consider the modality.
And it's going to complicate. I think it's going to complicate things a lot for the designer. I think we should leave up to the IC, and at least that's my opinion, that it should be left up to the IC designer to provide something that's frequency dependent, period. A number that's frequency dependent. That is it, regardless of the nature of the interface.
Okay. Yeah. Okay. I'm fine with that. I just wanted to understand a little bit the details. So apart, would this be applicable to analog supplies only, or you would do it with the core as well?
This what I'm saying here for noise mask is mostly for analog supply. For core, typically it's a lot simpler, where it is like, I don't know, millivolt peak to peak for DC, and then everything for high frequency. For core and rail is typically it's a lot simpler, because they don't have the sensitivity to clocks. They just have to close timings, and for them it's like it's a millivolt peak to peak.
Okay. But it will be still, you would have a table. Just the table is going to be a lot simpler. So maybe with one value that says peak to peak this much. Thank you very much.
Yeah, it would be like a DC plus or minus a tolerance.
Yeah. Okay. And would you express that okay, now that we are talking about core, would you express it as millivolts or as a percentage of the supply voltage?
Either way. I think either way is fine. Typically, suppose somebody would say, hey, 0.75 plus or minus 3%, which is very typical, the number 3%.
Yes.
Or say, I don't know, 0.7 volt plus, when it's not symmetrical, you can say plus 0.75 volt plus 20 millivolt minus 30 millivolt or something like that. Sometimes it depends.
Yeah, I'm thinking right for the core, if you have DVFS and you're scaling voltage and frequency, would it be still one? Would it be one table that says plus minus 3%?
In that case, if you have DVFS, it's likely not going to be percentage anymore. It's probably going to be a fixed value, like, I don't know, just 15 plus or minus 15 millivolt plus or minus 20 millivolt.
And okay, so you would apply that to all voltage levels. You would want to have that fixed value.
Yeah, typically, right? Because DVFS doesn't deviate from the DC voltage that much, right? It's like the DC voltage in DVFS in the dynamic voltage scaling doesn't change by a big percentage. It's probably, I don't know, 5, maybe 10% at most change. So that yeah, it would be typical for what the experience that I have is like the typical AC voltage is fixed over the range of the DVFS window.
Okay.
I mean, of the DV window.
So that means that whoever does sign of timing, they will need to, they are signing off high voltage plus minus say 50 millivolts, and then at the lower voltage they're signing off still plus minus 50 millivolts with the lower voltage. Is that do you understand that correctly? They would not scale.
Sorry, I didn't get a question. I didn't get at this question.
Say you have two power modes of your chip, right?
Mm-hmm.
It runs at 1 volt, 1 gigahertz, and then it runs at 0.5 volt, 100 megahertz, right? When you go and do timing sign-off, right? It's your high voltage. You would do plus minus 100 millivolts, right? Say it's plus minus 10%, right? So you do plus minus 100 millivolts.
Mm-hmm.
And you do it at 1 gigahertz. Now, my question was at the 0.5 volt, when you're signing off at 100 megahertz, would you still do plus minus 100 millivolts, or would you do plus minus 10% of the 0.5 volts, which would be plus minus 15 millivolts?
That's really going to depend on the. That's really going to depend on the on your timing that the IC design has, which will specify. I've seen both. I've seen 0.5, like you said, plus or minus 3%, and then 1 volt plus or minus 3%, and I've seen 0.5 plus or minus I don't know, 25 millivolt, or plus minus or minus 50 millivolt, 15 millivolt. So I think I don't think it will be you'll be putting constraint to decide whether it's a percentage or an absolute value. I think it should be left, given the option to have either millivolt, absolute millivolt, or percentage of the nominal. Especially like you say, you have cases where the voltage, if it is not core, right? You're talking about, for example, on the DDI interface, where LPF interface, whether you're running at a low voltage or high voltage, where the nominal is a big difference, is a big swing. So yeah, I think I think it's best to leave the option to have either the percentage or the absolute.
Okay.
Tolerance.
Yeah, let me calculate it. Actually, okay. Let me just have this clear. Okay. But they and that voltage swing is the chiplet bumps, right?
Yes. Typically the IC will specify the voltage at the bump, and
Okay.
now it is up to the system designer to design their package. It depends. We're talking about a chiplet, right? So I don't know. Again, I don't understand enough the scope of this. If when we say chiplet, we define all the chiplet on an MCP, and then we're looking at the balls of the package, or if we're defining just the chip itself, and then we're stopping at the C4 of the IC. Regardless, the IC designer, they will give you a specification at the C4.
Yes. Yeah, exactly. So the scope is actually all of the above. The idea being like this, right? In one case, you have the designer of the silicon chiplet, right? And that's their product. And they will put the requirements because they only see their chip. They don't know what else is out there. They put the requirements and description of that chiplet. Now, the next level system integrator, I'll call it just integrators, right? They will integrate multiple chiplets in some way, in whichever way they want. And then they will generate a new part, a new product, right? In that case, they will put that kind of descriptions on the boundary of their product. And that product then could go into the next level hierarchy. Right?
Okay.
So somebody could take chiplets from here, chiplets from there, put it on silicon interposer, and generate technically a 3D stack silicon fast. But for the next level integrator, that would look like a chiplet, right? Like a silicon piece. They don't need to care how that's implemented inside, or they would only care what are the requirements on the chiplet fins that they need to meet, right? So my expectation is that the integrator that did the integration into silicon interposer, whatever simulation they run, whatever requirements that they have met, they'll describe those at their interface boundaries and hand that off to the next level integrator.
Okay. Yeah. So in that case, right? So in that case, you're talking about both the chiplet boundary and the package boundary here, and the voltage definition should be the same. It's just that the tolerance might change a little bit.
Yes. Yeah, because that would depend on their simulation, their integration. They've met their implementation needs, the internal chiplet limits, but they mix it with other external limits, right? I guess they could meet the 3% voltage swings to the internal chiplet, but once they put it on the silicon interfolder, they may say for the next level guy, hey, you have to meet at 2% PPP, right? Because
Yes.
I'm losing something on my end. Okay.
Yeah. So exactly, right? So you're going to provide something tighter at the balls level, and then it's going to pick up more noise or more drop on the package, and then you have to specify something a little bit looser at the C4.
Yes.
And of course, the designer knows that on his PDN inside the IC, he's going to lose there and generate a lot more noise, so he's going to be even looser to meet his timing.
Yeah, exactly. Okay. Yeah, this is good. This is good. Thank you for the comment. We sorely needed someone to help us on the product development side of things. So I'm glad you came back.
Okay, I mean, again, I'm more than happy. I'm more than happy to provide whatever help is needed to make this a better document. So just let me know.
Yep.
And again, I have to admit that I do not understand the entire concept. I'm just joining this sporadically. It's probably my second or third call. I don't understand the entire concept. I mean, the entire high-level flow, but just let me know.
Yeah. Let me give you a little bit of preview. What our thinking is. This is part of the what we call PDLC design kit. This is I'm gonna mention this at the global summit. So we are talking about a
This is
PDLC
this is for the upcoming summit or last year?
this is for the upcoming.
Got it. Okay.
I've covered some of this already. So basically, there is several pieces that come into the PDK. Right. What we're looking at is so we did the CDK. CDK is fairly straightforward. That CDK describes two pieces of information. One, it describes the chiplet dimensions and bump locations, and it describes what other models are provided by the vendor. Right? Does the vendor provide IBIS, Liberty, a gray box variable, things like that, right? Just a metadata of what other data is being provided. The material design kit, this one we completed already, describes basically it's a set of materials. And each material is described by its properties, by the relevant properties, right? Electrical, mechanical, thermal properties, and so on. Things that you would use for simulation. Right, electrical properties, for example, for the package, right, it would be DKD, mechanical properties would be sticky, thermal conductivities in there, heat capacities in there, stuff like that. The assembly design kit basically describes how chips are put together in space, right, into that product, right? How is it flipped, how it's rotated, in Z dimensions, are they sitting on top of each other, how they fit in on top of each other, and so on. The test design kit version 1.0 is fairly straightforward. It just says, hey, do from all the pins that we had described in the CDK, which by the way also has the power supplies in there. The CDK has the power supplies, but of all the pins that are in CDK, it basically if you single out all the pins which are used for test mode. And it will be very very simply describe, hey, here's a test mode, and in that test mode, this pin is a 12, and these are the data pins, and these are the data pins. Really simple stuff. And for version 2.0, we are looking to add a little bit more data into that. With the idea is to enable the actually automated integration of automated test insertion flows for the integrate It describes what the paths are, some timing information, and so on. Now, and this is where the SIPI kit comes in, right? It basically describes on the SI side, it describes interfaces in terms of what they are, what is the electrical protocol, what are the electrical requirements of that interface, and it identifies between the pin respondents. And the idea is, typically today when SI simulations are being run, you have a user who have to go and read a whole bunch of data sheets and to populate the simulation tools. And we want to automate some of that population part, right, to prevent any errors that may happen. And you can, I guess, what Mark was saying is you could potentially describe a virtual interface, right? That is UCAE and say, here's UCAE and these are the electrical parameters. And now you can start running simulations against the channel limit. And see if those do, right? You can create a virtual chiplet and see whether your channel whether your channels are good or not. Or you can have actual chiplets and run the simulation to the actual chiplets. On the other side, once we have the interface description, and actually that's the pie part of the interface. So once we have the file descriptions with the electrical properties, you can quickly do a sign click here that two triplets can talk to each other. Right? They may have requirements, signal integrity requirements, which are just not compatible for whatever reason, right? And then the PI is also part of that. In a way, the idea is to describe what does the integrator need to do. What are the limitations, and what does the integrator need to do in order to meet PI for the chiplets? And I think what you mentioned, I think those supply swings, that's important piece. I know for there's some expectations on impedance and actually I'm not sure the impedance is the right word for the power plant. Anyway.
Yeah, the impedance noise mask. I mean, you can also some vendors, actually some IC suppliers also mention impedance and stuff like that. But I mean, I think it really depends, or it can get complicated. But I think for me, the easiest way to do that is just provide the voltage requirements.
That's right. I think all their chips will probably talk about impedance and capacitance requirements, and chiplets where you have zero view into the next level integration technology. You really cannot put, you really cannot say your impedance and capacitance must be this much, and instead, as you said, this is the noise you have to meet. How you do it, I don't care, right?
Yep.
Yeah. So this is where the SIPI kit fits. And the third one, actually not the third one, the last one is the package diagram, right? That describes stack up materials, routing rules, power planes, all that stuff that is basically that DRM was run from the subsidiary manufacturer. What are their rules? And then the implementer basically will take that DRM, will take their material design kit, we'll talk to the assembly house, see what their assembly limitations are. We'll get from the chiplet vendor their SIPI description and PDK and CDK and put the whole thing together.
Okay. So a quick question. So what's the status of all these 6 swim lanes, for example? Yeah. So today we talked about the SIPI dev kit. I mean the DK. The status of the remaining 5, are they already like defined, or are they in the process of being defined?
So SIPI is we are working on right now. TDK 1.0 has been completed. We are working on TDK 2.0. And the way we do it, actually, CDX, we alternate each week. So this week is SIPI, and 2 weeks is going to be SIPI again, and so on. PDK is going to be next week.
Okay.
And DRM is something that we are yet to start working on. The other three are done, right? Well, I guess these three are done, and version 1.0 of this is done. SIPI, we are yet to publish 1.0. We are working on version 2.0 TDK, and DRM will start working. As soon as we get one of these, whichever gets done first between TDK 2.0 and SIPI kit. Once we get done with that, we'll reuse the pencil to work on packet DRM.
Okay. All right. Thanks.
Yeah, and kind of the idea of all these pieces is how do you sit right? There's you probably know a lot of the architectural, a lot of stuff gets done, and pretty much set in stone, and all of these kits get used across different pieces, and then at the end you do the design and you do sign off.
Okay.
Yes, that's what the thinking is.
All right. Okay, cool. I mean, I see that there's a lot of work has already been done, and it definitely is just on the trailing end, on closing on the SIPI, the DK. So yeah, super.
Yeah.
I'm trying to see if I will have time to make it to the conference in June, in October. So definitely will be there listening during the presentation. But yeah, whatever, let me know. Let me know if anything I can do to contribute to the SIPI, the DK document that you were working on today.
Awesome. Yep, I will. Thank you.
And I think from here you can. I mean, I don't know. From here you can have my email. I suppose though, right? So, if you need, if we need to exchange emails, that's fair.
Yeah, yeah. Have you signed up for the Groups IO mailing list?
What was that again?
The Groups IO mailing list, CDX.
Yes, I think I am on the mailing list, right?
Okay. Good one.
No, I'm not here. I don't see my name here.
Okay. Well, let me send you a link to this. This is our CDX mailing list.
Okay.
I'm posting it in chat. Here's how you sign up, right? You just send email here to this link. Just send email, empty body, empty subject. No need to send anything else. And
okay, got it.
It will happen.
So yeah, I'm going to go on the OCP, but since you are here, can you type this in the chat window so I can pick up the subscribe list there?
Oh yeah. So basically, if you go to that link I sent, you will see this page.
Oh,
and
you sent a link. Sorry. You already sent it. Yeah.
Yes,
I got it.
yeah. Yeah. Okay.
Okay, subscribes. Okay, yes, I'm going to do that. Thank you.
Yeah, you're welcome. All right, everyone. I think we're getting close to the end of this meeting. Any last thoughts or comments? Mark, Boom?
Nothing else from me, thank you.
Nothing from me.
Okay. All right, then we reconvene again in 2 weeks to talk about SAPI. Next week is PGK 2.0. So I'll see you all next week then.
All right. Thank you, guys.
Hey, have a
Bye.
good holiday weekend.
Thanks, everyone. Oh, yeah, you too. Have a good one.
Thank you. Bye.
Bye.